Welcome to Lunch and Learn with Industry. Our talk today is Machine Learning Jobs, What Are They Like, and How Do You Get One? By Joe Dumoulin from Aon IP Services.
Welcome to one of the webinars from the Lunch and Learn with Industry talks. My name is Venera Arnaoudova. I'm assistant professor at the School of Electrical Engineering and Computer Science, and I'm here today to introduce our speaker. Joe Dumoulin is a software engineer. I think he has more than 30 years of experience in software engineering, with 20 of those being as a machine learning expert. And he's today a senior research scientist at Aon IP Solutions. And he is here to talk to us about what do you need to know to get a job in machine learning. Joe, without further ado, take it away.
Hi, thank you. Thanks everybody for showing up. And I'm going to try and burn through these, 15 slides or so that I have here and talk to you and get a chance for you guys to ask some questions if you want. But basically, like Venera said, I'm just going to talk about what you need to know to get a job in machine learning. And I got a little image here. I'm kind of curious if anybody knows what this is. Some of you probably heard me talk about it a little bit if you were on earlier, but kind of curious. If nobody has any questions, I'll ask you guys if you could tell me what this is here. It has something to do with deep learning. All right. And let's see if I can make this thing work here. Okay. So I'm going to talk about jobs, and the first thing to do with a thing like AI or machine learning or data science is where would you go if you wanted a job in this kind of thing? Like what kind of industries could you work for? And so this is, of course, a thing that changes all the time. But what I'm going to do first is talk about there's a few industries where this is important, and they're grouped in, I group them anyway, in this way: professional systems and services. So that's like enterprise resource planning, analytics, finance, and health services. These are big companies, really well established, even like factories too. Okay, I should have put that in here as well. These are like industrial type of companies, and they're very traditional. But what they've done is realize that in order to compete in the modern world and to be able to use some of the decades of data that they've collected around, processes and customers and so forth, they need these techniques in order to do this. The techniques of modern AI, like machine learning and data science, I'm going to use AI kind of interchangeably with those. And in some sense, this is wrong, but just bear with me, because the fact is that everybody else uses AI that way. So I'm going to too. It took me a long time. I fought my way through that one, but eventually I lost. So then entertainment services, this is something we all experience mostly on the web, right? So Facebook, Twitter, Netflix, Spotify, and many others, right? There's all the online broadcasting tools like YouTube, that sort of thing. All of these are heavily invested in AI around what people are watching, how many times things get watched, what are the availability. Like at Netflix, is the movie available to watch? Those are really big problems that are handled using statistical methods. And then consumer services. So like on our phones, we can do banking and shopping. We have health applications, and we have like IoT home applications as well, right? So these are other areas where right now AI and ML are like, this is the thing. Everybody's building up a set of tools in this realm and then hooking them up to web services so that people interact with these tools, and then the tools provide feedbacks in some way. All right. So I won't go into any more of that unless there's questions at the end. But the idea is that each of these types of systems has different, sort of provisioning for data analytics, data science, and machine learning. And what I'm going to do at this point is I really just want to talk about the types of jobs that are available in machine learning and data analytics today. And these are jobs that are present in these types of industries and others. And of course, next year, if I did this talk, I'd probably I very likely would have to use a different set of industries to talk about it, because this changes constantly. But right now, these are the big ones. And if you're looking for a job in machine learning or in data science, these are the kind of the landscape of companies that you'll want to look at. Okay, and we can talk more about that later. But first, what I'm going to do really for the most of this talk, what you'll see for most of the talk from now on, is a discussion of these 4 types of professional jobs that people can get today in this area, in this realm. Okay, so this is kind of a grouping of job titles in some sense. Okay, and these 4 job titles are, I chose these because they're separated enough. Within each one, there are different levels, like there's a junior analyst, there's a senior data scientist, there's a senior, machine learning research scientist, whatever, okay. And there's, different levels of engineering skills for each of these tasks, right? The different educational requirements for each one. But I'm going to talk about all 4 of them in the context of what are the tasks that somebody in this area would perform in a machine learning context. And then what kind of maybe architectural decisions do they have to make in their job? So you can kind of think of it as like, what I'm going to do is propose sort of a fake job description. But if you were to go onto Indeed or some other job search area or talk to a recruiter, these are the kind of jobs that they need, whether they know it or not. Like the recruiters often might not have any idea what they need in AI, but they know they need some AI, okay? And so they're looking for people who can do that kind of stuff. What you really want is, understand the job description from underneath, and that's what I'm going to try and do today. So the 4 categories are data science and data analytics, machine learning and AI, high performance computing, and I'll talk a little bit about cloud computing. These last 2 areas are not my area of expertise. Now, I know a little bit about them just because I have to, but the fact is that most serious machine learning shops have specialties in these areas, in all 4 of these areas. And what you'll do is interact as on a team when you're building a machine learning tool, or when you're building a full application that has machine learning tools inside of it. Think about self-driving cars, right? There's a huge software component to a car or a self-driving car. And then at the same time, there's big machine learning side of that is like perception and action and that kind of stuff. All right, so I'll talk a little bit about what is involved in each of these 4 categories of jobs. Does anybody have any questions before I go too much further? I just want to know if anybody's got any, if I'm making sense, I hope. So it's so difficult, right? Like I love to do talks on the whiteboard and then people can yell at me, but in this context, it's a little bit, there's less interactivity, so it's a little bit hard for me to understand exactly how this is coming across to you guys, but I'm hoping that you'll, put your hand up virtually or shout at me virtually if you want to know. So let's talk about data science a little bit first. The kind of tasks that are included in a data science job are collecting data, cleaning data. Okay, so you can collect some data from your industry. Let's suppose we're talking about Netflix. You got a job at Netflix, a very good data science machine learning shop, and they pay very well and have really interesting problems. And you go in there and you got to collect some data for a particular problem. There will be lots and lots of different choices. So you have to know how to get the data, how to bring it in a way that's appropriate for answering the question that you're starting with, right? Because typically as a data scientist, you'll be given a question to answer or a set of questions to answer. And then you try to develop some way to do that. I'll try and share some examples as we go. And then cleaning data. Once you've got the data together, the data is going to have a bunch of stuff in it that you don't need. So you got to figure out how to get rid of it. Also, your data will have missing pieces and it will have incorrect entries, things that are glitches or somebody entered something wrong. You have to figure out where those are and fix them as much as you can. So data is a messy thing. It's a very real world, messy problem that is a lot of times in the education environment, you don't see very much of this. You might see it in a specialized course, but like when you take a machine learning course, most of the data that you work with will be pre-cleaned, very nice. It will present something that you can work with in a very straightforward way. Once you've cleaned the data, you need to pre-process it. And this really amounts to doing some mathematics on the data. So for example, you might have, suppose you wanted to predict the price of houses, okay? So a house, maybe you want to say, I want to predict the price of houses based purely on their square footage. That's a pretty reasonable thing to try to do. The problem is that the square foot of a house and the price of a house have different sort of dimensions. One's an area, and it increases and decreases at sort of a different scale than the price of the house. The price of the house has a large scale, like it may have a large range of movement, but basically they're on, the two move on different scales. So you can do that training and it will probably work okay. But a better way to do it is to take those two sets of data and scale them so that like the maximum value and the minimum value are between 0 and 1, for example, in both cases. Then what you'll find is your range of machine learning options is very much wider because the data is scaled in such a way that the two, like the price will move up and the size of the house will move up in a much more well-scaled way. This happens a lot in data science, and we see this effect of this in, for example, logarithms, right? Sometimes you have logarithmic increase in a value. If you take the logarithm of it, then you get a linear increase in the value, and that makes it easier to do the estimation. So folks that do like experimental statistics see this kind of thing a lot. So pre-processing is a very important part in order to increase your options for what to do with the data next. Next, you want to find ways to store the data. This sounds really simple, but in fact, there's a whole bunch of parts to this. A lot of it has to do with databases, how they're structured, what kind of data you have and how it is structured, and what kind of questions you want to answer with the data. So the structure, the structure and the context that you've gathered the data in matter for how you store the data. If you've ever taken a class in RDBMS or SQL, this is kind of what's going on there, right? You learn SQL in order to understand how to design a data storage that makes sense for the types of questions you need to answer, okay? So there's like a context, a semantics that sits around your structure of your data. And then of course, the thing to answer questions, you have to access that data and visualize it. A lot of people aren't going to be able to write SQL to get into your data. So the better you can get at visualization, the better you can get at sort of making it easy for people to understand how to access your data, the better off you're going to be. So some of the architectural issues you're going to run into are streaming. Okay, how do I get new data in? After I've done all this work, do I want to continue to update this data? Does my question need to be answered, daily, weekly, every quarter? And then availability. Is my system available when people need it? This sounds again like a simple question, but in computer land, it is not. Computers fall over all the time, and trying to make them build things in such a way that the computer stays available is actually a very challenging part of this work. And then data changes over time. You build up a data set to answer a set of questions. Next year, we still want to answer those questions, but we want that data also to answer other questions. So we will change the schema to correspond to the new questions we want to answer. And that has to be part of the work as well. So there's an evolution of the data source, of the data that I'm storing, okay? And then scalability. Can I store all the data that I need to and then still access it in a reasonable way, right? I mean, in a reasonable amount of time. I work with a lot of data sets that the guys that do this work, like it takes days to process the data and get it into a database that then I can use to do my work. And most of the time that's okay, but as time goes on, you get these order one, sort of like constant time is what you would like to have, but you get these linear time and quadratic time increases in the amount of time it takes to get the data into the database. That's not scalable. And so a lot of the work is trying to figure out how to bring in the data in a way that's scalable over time. Also to access it, as the database gets bigger, queries take a longer time, visualizations take longer, and that makes it harder for people to use. All right, so these are all sort of architectural tasks and the kind of things that you're going to be doing in a data science type of job. Let's look at a machine learning job for a second. And this one's a little more involved. I mean, it's really hard for me to be like terse about machine learning because I've been doing it for a really long time. And there's a lot of things that are possible with it. So I want to kind of give you an idea of that. So the same is also true of things like data science and of like high performance computing. These are huge areas with lots of rich problems to solve. I just happen not to know as much about those areas. I mean, I know enough to get by, maybe enough to be dangerous. That's what my colleagues would probably say. But the idea is that I know more about this, so I'm going to talk more about it. So there's three basic types of machine learning. Unsupervised learning. This is where we want to group or compare data or make a recommendation of new data from old data that people have looked at. Supervised learning. This is where I want to predict or forecast based on the past. Like I want to take in a bunch of data based on the past. I want to use that data to find a way to predict what's going to happen in the future. And these are, we can talk a long time about that. I'll let that drop on the floor for a minute and we'll come back to it if there's questions. And then there's this idea of reinforcement learning. This reinforcement learning also applies in many of the contexts that supervised learning applies in, but reinforcement learning is a little bit more complicated. It's more about building up systems that can plan their behavior and that have like a set of behavior that they know about certain like state transitions that they know how to do. And what they learn is what the data looks like before a particular state transition should happen. And that's a sort of complicated way of saying it, but if you just think about, again, a self-driving vehicle or an autonomous robot, okay, basically what they're doing is they're making plans about how to move through the data or how to move through their environment. And they are using past data that they've learned before to decide what the next motion they should do is, okay? And that's all done automatically, and it's done through this idea of reinforcement learning. This is again, a rich area. It's also quite difficult, so it's not done except where it's really needed. But there are some great areas for this reinforcement learning. Forecasting and investment, this is a very big deal in financial areas, although I have my doubts about how well it works. I'm not directly experienced with it for a long time, but for about more than 10 years now. But it's probably more, it has a sort of a built up reputation that it maybe doesn't deserve. Okay, I'll just leave it there. So here's a little bit more detail about supervised and reinforcement learning, okay? And the idea here is just what's the cycle of work that somebody who's doing this type of thing has to do. Basically, you have a predictive task that you define with some, in my case, with some business users, okay? I work in intellectual property, so typically it will be with lawyers or scientists from a client company. And we'll define a task that we want to perform. We want to predict something. And then we'll go and collect the data, okay? Remember, the data scientist goes in here. So at this point, I would work with a data scientist. We would find some data, collect it, clean it, store it, okay? Part of that process will label the data so that we know that for each given instance of data, we have a label that we know what we're coming out with. So I talked about the house price thing a while ago. If I wanted to build a system to predict a house price based on some data about the house, like maybe how many bathrooms it has, how many square feet it has, what neighborhood it's in, okay? Those are all sort of parameters of my data, but then I have the actual price that a house sold for is the label that's on the data. So if I have a bunch of data about previously sold houses, I can then build a prediction engine for what I think the other new houses or houses that haven't been on the market would sell for. So think about Zillow. Okay, Zillow is a company that does this. And they are heavily invested in this machine learning, this type of machine learning. So then once I've labeled the data, then I can show it to a model and the model can train. So this is an example here of a simple multi-layer perceptron neural network, okay? And here what I would do to train this network is I would apply the input data as this X1 through X4. And then what it would do in training is it would train, there's numbers associated with each of these gray lines, these gray arrows, and each one of these has a number associated with it called a weight. And what the training cycle would do is read each piece of data in, and then it would check at the end and see if the label is correct. If it's not, it would create an error for that. and the error has some value, and then it would propagate the error backwards and adjust these weights on these gray arrows. So it's basically this process of iterating over the data and adjusting these weights until they converge. When they stop changing, my network is trained, okay? So it's really just an iterative computation problem. And it's linear, I mean, it's linear at each layer, so it will converge. Mostly for a MLP, it's pretty difficult to get one that doesn't converge, but they often will converge to the wrong thing. So you have to, it's not quite that simple, you know, that you have multiple points of convergence. I'm not going to get into that, but basically the idea is that you can train this model, and all of the training is training the weights on these lines. Each of these lines is going to represent, or each of these areas in here is a layer, and they represent a matrix, right? So this is a matrix of values. This and this, if this is 1, 2, 3, 4, 5, and this is 3, I have a 5 by 3 matrix that represents all the weights in this layer. Here I have a 4 by 5 matrix that represents all the weights in this layer. And basically that's how neural networks work. They're all like this. They're just bigger, okay? This one just happens to be tiny. So we train that model, all these weights stop jiggling, they're all fixed, we're ready. So then we test the model. I left that part out, but there's a test phase, of course. And then we have deploy, the model's out in the world doing its thing. And of course, what happens is it's starting to encounter real data. Real data is different than my lab data that I use to train the model. So things happen, especially over time, things change. Sometimes the model's prediction will change the input data, depending on if the prediction is used to generate new data that comes back into the model. Okay, at some point I have to go back and recollect data and retrain the model. This happens in a cycle constantly. So as a machine learning engineer, okay, this is what people do. They collect the data, train the models, deploy and monitor the models, and then collect more data and do it again. And this happens over and over and over and over and over. Eventually, you know, if you're at Netflix or Facebook, the models might change over time, or multiple models would be in play at any given time, and they'll compete with each other. Sometimes they work together to make a decision, but basically this is the path that you would do as an engineer doing this work. It's a very interesting, mentally challenging job. Okay. Supervised and reinforcement methods encode human expert knowledge and make it available for everyone. For example, think about asking an app for driving directions. Okay, so driving directions is sort of an expert task, right? If you go to a city you've never been to and you try and drive around, it's really hard. It's hard. I've done this a lot. And in the 90s, when you did this, you had to have maps. And you know, think about looking at a paper map and driving at the same time, trying to get through a city that you've never been in before. Okay, this is terrible. So nowadays we have some app on my computer that talks to me and tells me where to go next. I mean, that is a game changer. Okay, that is really great. And what I'm doing is I'm capitalizing on the expertise of all the other people that are driving, people that have been driving in this city for all their lives. And I get the advantage of that. So that's the idea. That's sort of the ideal place for this kind of learning, is like, how can we share knowledge that used to be in the confines of an expert or in this book of deep, you know, mathematics or something that I need to know, engineering science that I need to know in order to do that task. Now I have access to all these tasks. Let's look at unsupervised learning for a minute. In unsupervised learning, it's very similar to supervised learning, except that it's really an analytics task, and there's no labels on the data. This is a data exploration task. So sometimes this is really more in the realm of a data scientist than in a machine learning guy. And in fact, that's often the case. But the truth is that many machine learning tasks include unsupervised learning tasks as well. So that's a little deeper topic than we can get into in this time frame. But the idea of unsupervised learning is to take a raw set of data, run it through an algorithm, and cluster it to see like what kind of common things are happening in this data. So in this case, this is being clustered. This data here is some patent data that's being clustered based on the abstracts of the patents, right? So you can think about this for any document that has like an introduction, a short introduction. And we come in here and we have all these ones that are about communication and packets. And down here, we've got autonomous vehicle and environments. And then up here, we've got lighting and a light signal. So this looks like it's data from some kind of self-driving car company, patents around self-driving cars. But the idea is that patents in these different areas, these technology areas, are automatically sort of sorted together by the algorithm that's being used. The particular algorithm in this case is called DB-scan. It's like a, oh, what's it called? Anyway, we can talk about it later. But it's basically a neighborhood method. It's looking around a neighborhood to see if there's close points, and everything's treated like a geometrical point. So here I have these parameters. What are the parameters in this problem? It's every word in the abstract, okay? That's the parameters. So what I'm doing is building this representation for the words, okay? And then I'm comparing each abstract's full word representation to each other one, finding the ones that are close in this, what is essentially a vector space, right? I'm creating a vector for each of these abstracts, and I'm looking for other vectors that are close by, and I'm grouping them together. And then I'm separating them from each other with some kind of a threshold, okay? Some distance that's too far away for them to be near neighbors, okay? And I get these three abstracts. So, you know, I hope it doesn't sound too complicated the way I'm describing it. It's actually, there's tools that make this possible. So we use a tool called HDB-scan to solve this particular problem. But this work is being done in very high dimensions. We're showing this in 2 dimensions here, but the vectors that are being used are 700 dimensions. And the actual clustering is being done in 15 dimensions. So there's a dimensionality reduction step. So it's called a subspace decomposition, right? So this is all, if you want to know how to do this kind of stuff in the sort of the scientific approaches to doing clustering, these are all linear algebra terms that I'm tossing out here, and they're very common to sort of a linear algebra background. This kind of takes these, what 10 years ago, well, maybe 20 years ago, were very sort of abstract linear algebraic concepts, and it makes them very relevant to doing this kind of work. So like I've got these patents here from some company. This may be work by a company that wants to buy another company. So they want to see all the other company's patents before they buy. So we'll organize them into this kind of view, okay? And I hope that makes sense, but like this is real world, you know, real money type of transactions being done with very deep mathematical concepts. So what do we do here? We want to collect data, do the analysis, visualize, that's what we see here. And we want to provide ways for people to interact with this data. So you might want to come along here and like look at individual patents in this grouping. So we would have a little pop-up box that lets you do that. We show keywords here because there's no labels on this data. We don't know what this cluster is. So what we want to do is find some keywords that represent this cluster. And that's a big part of what we're doing in this exercise here. And then we want to monitor again, because as we go along, we know that new data is going to be added to the system. And so we want to, even though we might save these models and use them for, if we drop a new patent in, oh, they had 10 new patents. What technology areas do they go into? Put them on and they would show, you know, this becomes like a trained model. But over time, we want to retrain the models and show new visualizations, okay? So you can see that all these different types of learning kind of are similar. Unsupervised methods are really built as assistants to people, right? The idea is that this is going to provide a already expert person with some tools to do more analysis, like to better accomplish their job. So those technology area mappings, like what do they do now? So a lawyer, an analyst will hire a bunch of lawyer temps, you know, folks in school, to read a bunch of patents and then to physically move them into different categories, okay? But now we have a machine learning method that can do it automatically. And then they can look at the automatic separation and just decide if it's okay. They can still look at the individual patents, but now they've spent an extra 2 minutes for the machine to do the first organization. Then the experts can come in and do whatever they need to do. It's not really replacing people, but it's helping them get to the next stage of their work in a faster way. Okay. So with data science and machine learning, there's a whole bunch of like technology around this, right? And so I'm saying tools of the trade so far because we're really just kind of looking at a snapshot in time that's, you know, November 2020. And so last year, was it last year? Oh man, I think it was 2 years ago. I did a talk at WSU about natural language processing, so which is machine learning for written documents, okay, or chats or whatever, stuff that's written down. And when I wrote this long presentation, and then a week before I did the presentation, there were 2 announcements that completely changed the landscape of the technology, okay? So I had to add a new slide to show the papers from that, but they were like, they're so obviously important that it's like, this is gonna change everything, right? So even working with books in this environment can be very challenging because everything is changing so fast that you don't know. You know, somebody puts out some results, they're really good. You know, maybe 5 times out of 6, they're unreproducible. In other words, the results don't work really like they were advertised. There's a number of cases of that over the last 2 years. Really promising technologies that just don't work once you try and actually use them. But at the same time, that 1 time out of 6, there's something in there that totally changes the landscape again. Suddenly everybody's turned and moving this way with all the newest technology. It's incredibly challenging. But for a snapshot for today, you know, here we've got a couple of interesting things. RDBMS for data science, you need to have ways to store and manage data, and SQL is still the you know, sort of the prominent way to do that. There's a lot of alternatives to RDBMS these days, but this is the way that most companies do it, and it's the right way for most jobs, and that's my opinion, but such as it is, right? This is an 80s technology, but it works great. Another one is document storage. So there's this tool called Lucene, and there's been a bunch of tools built on top of it, and Elasticsearch is sort of the latest version of this, but it's basically document search. So if you think about Google and searching for web pages, Elasticsearch is that for documents, and it's the most prominent way to do it, and it's a very, very, very important part of any data science for natural language processing. For image processing, you're basically using the file system or something like S3 on Amazon AWS to store tens or hundreds of millions, maybe billions of photos, okay, or movies that you can then do the image processing on, okay? And then nowadays there's more and more of this time series data. In the past, most time series analysis has been done on very small data sets, relatively small data sets. Over the last 10 years, this has become problematic because most of the data sets are enormous. You think about logs of activities on a server, or financial transactions, that's the big one, of course. And quick, accurate time series analysis, health data, right? Managing your heart rate. Okay, look at how many of you have a Fitbit or some similar type of thing where you're going to be, you know, running and monitoring your heart rate while you're doing that. Those kind of things are all time series data, and there's now new databases that are being built to manage that specifically because it has its own special needs. And then we have some computing tools that are really common. Python and R are languages. Spark and Hadoop are really frameworks that are built off of the Java JVM. A lot of the work is still done in Java, but there's also languages like, what's it called? Scala, are very important in that context as well. With Spark, of course, Python is huge. R also is huge with Spark as well, although the Spark framework is still the Java JVM. And there's lots of other tools. Of course, we could talk about that for the whole hour. In machine learning, we've got a bunch of things to worry about. We've got hardware. So there's really 3 categories of hardware that are important in machine learning: CPU, GPU, and tensor processing units. This is a type of hardware that's been designed by Google. It's deployed on their on the Google Cloud, and is very powerful for doing operations for deep learning. All of these are, in fact. And there's hardware architectures that we need to worry about: multi-core CPUs, distributed compute between CPU and GPU, or multiple GPUs, or multiple networked computers. We need to look at architectures of our algorithms like SIMD, same information, same instruction, multiple data, and MIMD, multiple instruction, multiple data. And the idea here is, if I'm doing the same thing over and over again, right, in a pass, then I can pipeline my processes. I set up the code that has to be run, and then I push data through, and it just pipelines, runs through the pipe. If I'm doing multiple instructions, then I have to segregate different parts of the compute to do those different instructions. It's the only way to be efficient, right? And anybody that's studied this a little bit, you'll get into issues of cache. You know, how does the cache manage changing behavior when I change the instructions? Okay, when I change this data source, that kind of stuff. Languages: Java, Scala, Python, C++, R, tons. There's tons of them. And I'm sure next year there'll be more that are like important things that we would want to talk about, because they're starting to become important for machine learning. There's libraries for machine learning. I'm just talking about the Python libraries here, but there's so many. Scikit-learn, TensorFlow, Keras, these 2 are kind of together. And then PyTorch. Those are the big deep learning and machine learning sort of toolkits. There are lots more. There's libraries for mathematics. There's one called SciPy, which implements most important scientific algorithms. So if you have there's a book called Numerical Recipes in Fortran and Numerical Recipes in C. These are kind of classic books on the mathematics of engineering, kind of ways to implement that in computers. And most of those algorithms are implemented in SciPy. Usually, actually, they're really implemented in C++ and then given a Python wrapper on SciPy so that you can address them in Python. And then NumPy is the linear algebra library. It's where you build an array and then you say, multiply these 2 arrays together. And if you're doing it right, then it does it. If you're doing it wrong, it tells you why. Other important things are the Unix CLI, Unix and Linux CLIs, and the system architecture of Linux and Unix. These are nice architectures for managing the sort of the programming and hardware context of building big machine learning applications, because they really just stay out of your way. They provide nice tools to work with the system, but they don't get in your way most of the time. And the truth is you can do this on Windows as well, or other operating systems. But Unix and Linux seem really, for me, as I've gone through, I've been a Windows programmer for a long time in my life, but the Unix environment is just much better suited, in my opinion, for doing that kind of stuff. And of course, finally, math skills. This is like, it depends where you want to go with machine learning. If you want to go really into research, or you want to be able to solve complicated problems that are worth a lot to people, to companies, you need more math. If you just want to do machine learning and use the existing tools, you still need some, but maybe not quite as much. So if you're using tools like Scikit-learn, TensorFlow, Keras, PyTorch, and you're just building models that somebody else has designed, that's a real task that some machine learning engineers do. You probably will need to know a lot about linear algebra and probability and statistics. If you're designing large-scale machine learning systems that have to integrate with other software, you really need to know calculus, You need to know science of linear transformations. You need to know linear algebra and probability as well, but modern algebra also, very, very important. And these are all skills that, though they seem abstract, become very concrete in this world, okay? They're extremely concrete. I can provide examples for all of that at some point. So in high performance computing, I want to talk about this job as well. This is a super important job. And I wanted to bring up the fact, I didn't put the link on here, darn it, but there's a talk by a guy named Andrew Ng. He taught machine learning at Stanford for about 20 years. And then he went on to be the chief scientist at Baidu, which is like the biggest search company in the world besides Google. It's a Chinese search engine company, and he ran their machine learning department for a couple of years. He's also one of the founders of Coursera. Well, he said he did this talk to the Stanford Graduate Business School, where the title of the talk, you can go look it up on YouTube. It's called AI is the New Electricity. It's about an hour and 15 minutes long, and I assign it as an assignment in machine learning classes I teach because it's very useful for how to describe machine learning to non-engineering people, technical people, but non-engineers, okay? And one of the things that he mentions in that talk is how at Baidu, their teams always have a high performance computing and a machine learning expert melded together on the team. So an architect level high performance computing person, architect level machine learning engineer to design these very large systems that they're trying to train, okay? And this is an important idea because the hardware is actually so complicated, okay, that you really need this. So here we've got the tasks that somebody has to do in this world. They're going to be tasked with keeping the training cycles as fast as possible. Remember, they're iterative. So you have to iterate the whole network through all this data over and over again. And if the networks are very big, this step takes a long, long time. So the idea is how do we break up the task, break up the different parts of the system and to run as fast as possible to use as much of the hardware as it can while it's doing this task, scaling, streaming data loads. So I've got all this data coming in, more data that can be stored on a hard drive, right? Imagine that. We've got hundreds of terabytes of training data in a lot of text tasks. Or if you're training on images, this is very common, huge amounts of image data. So you have to stream it in, you have to batch it, and then train on it. It's a complicated problem. Finally, understand hardware features and new tech that applies to ML. So there's new technology coming out all the time. NVIDIA just announced A100. Oh, they announced the A100s in September. Now Amazon is building an A100 option into AWS, so you can go and use these new Ampere A100 systems. They're immense. I highly encourage you to go look it up if you're interested in this kind of thing, because they have these roomfuls of these A100 boxes that are, they're just incredible. The compute is really amazing on those machines. So the kind of architectural aspects of this job, you need to understand the computational behavior of these different computing units, right? The CPU, the graphics processing unit, which is now just really an AI processing unit, and then tensor processing units that are provided on the Google Cloud. These are specialized to Google right now, but they are very, very important to a lot of machine learning tasks at this moment. Not only do you need to understand the computational behavior, but you need to understand how that reacts to how that interacts with the cache in the computing unit, because computing units today contain cores and cache. They're really little distributed computing devices, right? So you have to be able to manage that. You have to understand memory behavior, especially how the main memory of your computer will interact with cache, how the main memory of your computer will interact with the memory of your graphics processor, okay? And how many graphics processors you have. Distributed computation, it's all kind of built in here. You need to understand like the SIMD and MIMD aspects of the architecture that the software has and how that's going to be implemented in the hardware. And then of course, network architecture. Network is the major source of latency in these designs. And so you have to really understand how to maximize throughput on the network. Pipelining is a huge part of these kind of designs, okay? I hope that's interesting. I thought a lot of the electrical engineers might recognize some of this, and that these are actually sort of scaled up network problems for you know, you know, like hardware designs, electronic hardware designs, circuits, is what I'm trying to say. So HPC is all about architecting large supervised learning training loads for maximum performance and minimum cost. This is a constantly evolving and very challenging engineering problem, as you could probably imagine. And here I just put a little example of a single computer and the kind of things that you have to look at here, right? So you've got data streaming in on the network. It goes to RAM. Something's happening on the CPU with it. So there's caches involved, and cache misses are very, 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 very expensive. You want to make sure that you're maximizing CPU usage. At the same time, RAM is going to be connected to the memory in your GPUs. Maybe you have 8 GPUs in the system. So then you've got memory associated with each of these, maybe, you know, 48 gigabytes on each of these CPUs. So you've got a very large array of CPU memory, and then each of these is going to be having some SIMD operation to chunk data through the network and train those to wiggle the values on those arrows that I showed earlier to try to get them to conform to what they need to train on the problem. Now imagine you have a data center full of these things, and then what you're going to do is you're going to go and say, all right, Amazon, give me 8 machines that look like this with 8 GPUs and maybe, you know, a terabyte of RAM each. And then network, you know, I'm going to have a network of them together. So there's probably some special network technology to maximize the network throughput. And then I'm going to try and build out my load, my deep learning training load, to maximize the use of that system. It's an extremely complicated job. Cloud computing is another task that gets in here. A lot of this these days is more you know, getting the right certifications and stuff, and maybe doesn't apply to the university programmer as much, maybe in an engineering sense or in a management sense. This is more of maybe a management type of job at this point for many of you that might be thinking about it. But cloud computing does have a lot of important aspects to this, and some of them are reflected in what I was just talking about with high performance computing. What we want to do is be able to understand storage, compute, and networking options for cloud providers. So you want to have a cloud provider like Google or Azure or AWS. You want them to be able to provide the loads, you know, the right tools for the loads that you want to do, that you want to run. That might be simple data science loads or really, really complicated deep learning loads. And you want to make sure that you have tools to create and monitor instances. Like maybe you have one person who's responsible for managing many, many instances that are running simultaneously. And those instances will change all the time. As training is done, we'll move on to the next task. You know, we don't want to do, you know, we want to have room for that. And then understanding the cost and availability of the options involved. So a lot of these jobs didn't exist 10 years ago. And in 10 more years, you know, they'll probably be completely different again. But there's new jobs and new titles being created all the time. And I just wanted to give you guys an idea of this. If you go look in the bureau, in the like the labor, Department of Labor in the US, that's when I was a kid. That's where we looked for jobs that we could go try to see if we're interested in. Nowadays, they don't have these jobs. You know, they have them, but they don't really describe what you actually do. And the things that you do are changing constantly. You know, this is not, the job I do today is not the same as the job I did 10 years ago, even though I might have described it in the same words to like my mom or something, you know? So I hope this was interesting. I know I kind of talked fast and I probably used up all the time, but if you guys have any questions and we have time to answer them, I'd be happy to stick around for a little bit.
Thanks, Joe. That was an excellent presentation. So for those of you who are here and you have questions, please write those down into the chat and we will do our best to answer as many as we can. So I'll go with the first question that I see from Andrew, how often do you typically have to retrain your models?
So it depends on the task. It's very highly dependent on the task. So if you are doing models for recommender systems, for example, you may have to retrain all the time, maybe weekly, okay? There's a lot of that kind of stuff. Like if you think about Amazon and Amazon too. Like if you're saying, you want to say like you bought all this stuff, you probably want to take a look at this other stuff too. Those kind of problems should be retrained constantly, right? Because people go through different periods of buying stuff, right? But for other tasks, like I work in patents and trademarks, there's new ones all the time, but basically the text isn't that different between different ones. So if I build some predictive models in that environment, I can reliably use them for some amount of time to move forward. I used to work a lot in chat systems, and chat language doesn't change that often. It changes fairly often, like within 2 years, the way people chat changes pretty dramatically. So you do have to retrain those models, but you don't have to retrain them all the time. So in that area, what we would do is build models that would run alongside each other, and we look at them and see which ones were doing better and see if it was time to change the models over, if that makes sense. But there's no real like complete answer to that.
Okay, our next question is, do you see a lot of movement in industry between more general software engineering jobs to ML jobs? And is it something you have to specialize for?
So machine learning jobs, you do need to specialize for them. There's a lot of tools for self-learning. So a lot of software engineers do move into machine learning. The challenging parts are really about the mathematics, and a lot of people like it's still early days. So a lot of the tools require you to understand, especially linear algebra and probability and statistics. But my own belief is that within maybe, I'm going to say 10 years, I don't know if that's true. It might be sooner or it might be later. You won't need that much specialized math knowledge to do a lot of this work. A lot of it will be, sort of managed at a higher level by the software. I don't think there's anything that keeps that from happening.
That was a great question. So I'll give them maybe a couple of minutes to see if somebody else has a question. I'll ask a question myself. So I really liked a lot the categories that you had for different jobs, and then what are the skills that you think are useful for one or the other. And I was wondering if you can talk a little bit more. So I'm assuming that you also do interviews and you're in hiring committees as well. And I was hoping that you can give some insights to the student. What are the strengths of the candidates that you interview for the different positions? So for example, if you were to finish a sentence like, a good or an excellent, for example, machine learning or AI specialist is a person that has such and such characteristic.
Yeah. Wow. So that's a great question. Like if you were to, I can talk to you about like what we do in an interview, like what an interview looks like for a lot of companies. I mean, this is not unusual. Like I've interviewed with Facebook and stuff, and it's pretty much the same in a lot of these places. The way that the interviews typically work is you talk to a recruiter. So it's very much like any software thing, right? You're going to talk to a recruiter. You're probably going to get a test of some type to do and then submit. And then you'll interview with a bunch of technical guys that will sort of critique what you've done and what it looks like. Very much like a regular software interview, okay? And then the next thing that will happen is there will be some questions about how you might do it different, what other techniques you might have used, why you chose this language model over that one, or this base, image processing model over that one. And then you would look at, how you fit in with the group, right? So there'd be interviews around teams, different teams you talk to, and see, they would sort of vet you and decide if you're a good fit for their team. And a lot of it is like, again, like any job and like any software job, you know, how you work with people is super important, and teamwork is a huge, huge part of this. As I tried to say, like all those different jobs, they're really not exclusive. All those people work together. And if you're a data scientist and you want to do machine learning work, entirely possible for you to do that. You just start doing some of that part of the project work because you're on the project with the machine learning engineers. And so once you get into doing this, and if you have a regular software job, again, there's a lot of ways to get into it, you know. But okay, let me try and address your question a little more directly, because I'm not really sure. Like, so for machine learning, you know, to be good at it, you have to be able to work in a team. You have to be able to, you know, it's constant learning. So you have to be able to continually learn new techniques. You have to be able to document your work pretty well. Okay. You have to be able to be responsible with like large money projects. So you're going to be responsible for spending maybe $20,000 to train a big deep learning network, maybe not even that big. But if you have a lot of data, it can take a long time to train. That costs a lot of money. And so you have to be responsible about that kind of stuff. You should be a good speaker, be able to talk to management and non-technical, non-engineering experts, right? There's a lot of questions. You need to be able to question people and say, what is exactly you're telling me? How do, you know, say something back to somebody? So, I mean, again, it's like any job, right? It's like what you're good at in this context is really the kind of things that I'm talking about. Mathematics, you know, getting the learning right for, you know, the models, designing the models, you know, doing architecture work. Everything else is really like other jobs. Does that answer your question?
Yes, I know it's a tough one. So yes, it does help. I think what you're saying is there's a lot of math. So if you're good at math, that's probably something that you might enjoy doing, right? And then it's not because you are good at math that you should be forgetting, you know, other skills such as communication and, you know, being responsible and being a good team player, which are, again, characteristics for pretty much any type of software engineering job. Right. I think that that is helpful. So I don't see any other questions.
I actually had a question.
Yeah, go ahead, Colin.
So I was wondering what you thought about like social media companies using machine learning to almost like manipulate their users.
Oh yeah.
And if you think there should be like a standard on how far that's able to go.
So I think about machine learning right now. Okay, this is a problem. That's a big problem. Okay. And there's other aspects of it. I mean, again, I think I talked with one of the ethics in engineering classes earlier this year about this very topic. Mostly I focus on like policing through machine learning or controlling people's jobs through machine learning. I'm not so worried about social media because it's a voluntary thing. People can just stop using it if they don't want to have this stuff happen. But the fact is that it is a problem. And what you're saying is exactly correct. The truth is I think about machine learning as like automobiles 120 years ago. It's like you can sort of hobbyish have one, and there's a few companies that make them and use them, but they're super dangerous, and there's not good rules around how they work. There's no traffic lights, for example. Okay. And what we need are traffic lights for the use of our personal data. That really needs to happen. Yes.
So you're just saying like it's so new still that we're still trying to figure it out. Yeah. Okay.
Yep.
Yeah.
And it's going to keep changing faster than we can figure it out. So if we go and just try and, you know, say, stop doing that, something else will happen. I mean, partly we have this whole internet thing. And so if you like, Facebook really only has network effects that keep it doing what it's doing. And it is designed, I mean, Facebook is only designed to collect data, right? That's all it's designed to do. So what they've done is set up a situation where you are encouraged to like things, and then they capture your likes and they know about you and they can use it to sell ads back to you. That's their whole thing. So then they now have all this nice data about you and what you like. They can sell it to other people too, or sell its use to other people. So Facebook's another one where they retrain their models constantly, right? Because they want to be able to, support this kind of feedback loop. Well, all right, it's pretty questionable in ethical terms. There's a lot of issues with that, and I think that they're remiss in addressing some of those at this moment. They're really struggling with this, and I think that their executives are not taking it as seriously as they need to. So that's my opinion.
Sounds good. Thanks.
Well, I would like to thank you so much, Joe. I learned a lot, and it was a fascinating talk, and I'm sure that our students did. So all of those talks are recorded. If anyone wants to rewatch it or you want to share the talk, it's on the ECS webpage. Again, thank you so much, Joe, for joining us, and I hope you all enjoy.
Yeah, take care.
Thank you. Bye-bye. Have a good one.
To learn more about the Lunch and Learn with Industry webinar series, follow the link in the description, and we'll see you next time on Lunch and Learn with Industry.